Hi, everybody. Welcome to week 4. I said my voice was okay, but it's clearly lying. Went to the doctor, don't have COVID, thankfully, just a very strained voice. So I'll try and get through as much as I can tonight without coughing too much. So we're looking at another method of analyzing organic compounds, trying to figure out what's there. So we're looking at infrared spectroscopy. And you can see the carbon atoms there are bouncing, because what we're looking for is the wobble. When we excite the bonds with a certain wavelength of light, they will stretch and they will wobble along the bonds. We can then measure this and determine what is there. So here we're looking at photons of light. Now, photons of light are very strange, as they act as a particle and a wave at the same time. Small massless particle. And the energy is determined by the frequency, or where it sits on the electromagnetic frequency. The far left, we have gamma rays, and then we have radio waves all the way over on the right. The closer you get to gamma rays, the lower the energy. The infrared part is typically where we look at infrared cameras, where we look at light. If you remember playing Call of Duty and the thermal scope, what you're actually looking for is the infrared radiation being given off by the heat source. So that's what we're using with this method. And it's not perfect. There are other methods like NMR that have been used or are used as well. But this is quite a simple, cheap option. So we have radio waves on the right-hand side that are the lowest energy. On the left-hand side, we have gamma rays. This is the dangerous radiation that's given off in nuclear reactors and by fissionable material. When we're looking at the infrared, and when we shine infrared and microwave radiation through anything, what we see is vibrating. It excites the molecules. Now, the way a microwave works is you shoot the microwaves into the food. They're not actually hot. What they do is they excite the water molecules. By exciting the water molecules, we produce heat. Smaller the energy, smaller the wavelength, the higher the energy. So unless you stick your head in a microwave or an infrared radiation source, you should be fine. Okay. What we're looking at here is the quantum mechanical energy levels. And we're looking at the vibration. So we have this vibration is perceived as heat. So covalent bond has a certain length. And this is done with an average because it's effectively like a spring between the two atoms. You can see that there. And what we're actually doing here, so on the x-axis, we have the number, the wave number even. So this is where we can see the number of times the light beam oscillates up and down. The more times it does this, the higher the energy of the light. We shine certain wave numbers of light or energy levels of light through a sample. We will make that the bonds within that sample vibrate and stretch and give off heat. What will also happen is these bonds will absorb a certain percentage of the light at the different wave numbers. Now, what we're looking at on the y-axis is how much light is making it through the detector on the other side of the sample. So, different wave numbers of light will be absorbed by different bonds. In organic chemistry, let's go to the whiteboard. We are looking for the following. We have, we have carbon to carbon, carbon to hydrogen, carbon to oxygen, carbon triple bound to nitrogen, carbon single bound to nitrogen. We have oxygen bound to hydrogen, nitrogen bound to hydrogen. What else we got? Anyone else? We've got carbon double bound to oxygen. These are the main ones. So what we do is we shoot a certain wavelength of light or a wave number, to how many times it oscillates, through a sample containing an unknown organic compound. What we do is we start at one end of the spectrum and you move through the spectrum. These various bonds are sitting in a solution here in our aliquot. Here's our source of light. And here's our detector. My very low tech drawing. So the light will pass through the sample. And what we're measuring is what we're looking for is what wave number of light has been absorbed. Because each of these different bonds, also got carbon to carbon double bond, carbon to carbon triple bond, they will all absorb a different wave number of light. And that's what we're looking for. So just remember that when we're going through this. And when one of these bonds absorbs light at one of these wave numbers, we get a reverse peak or a peak. If you flip it upside down, it would be a peak. And we can use our knowledge of what the peak looks like and the numbers that it corresponds to in order to figure out what's there. So on the left, we've got the percentage transmittance. So where the bond absorbs the light, we will see a peak. That way we can tell where or what is in our sample. So the CH2 group, it stretches and absorbs light at a wave number of 2,800 to 3,000. If it bends, it absorbs 1,350 to 1,450. Now, this is, all of these numbers are in your final exam. They are in your thingy. They are in your, oh man, they are in your formula book. But they are meaningless unless you know what it's supposed to look like. Many students at the end of their exam have said, I listened to you and I just didn't remember the numbers. Because the numbers are meaningless if you don't know what it's supposed to look like. So on the left-hand side, you will have hydrogen atoms. You've got your triple, double, and single bonds, or triple and double bonds in the middle, single bonds to the right-hand side. Now, in chromatography, the height of the peak told us the relative concentration. Completely useless here. It does not tell us the concentration. It just tells us what is there. So this would be done typically after you'd use chromatography to separate the sample. So, a strong peak is 2/3 of the way down to all the way down. So what we're doing here is we're using infrared light to detect functional groups. All of our functional groups have more than one bond. So we can use this, what's the word? We can use this pattern that we see to tell what is what. So these are the numbers you have in your data booklet. That doesn't make any sense unless you know what it's supposed to look like. And virtually everything is going to have, carbon to carbon and carbon to hydrogen bonds. So you need to look elsewhere to try and figure out what it might be. So on the left-hand side, we have bonds to hydrogen. Oxygen to hydrogen, nitrogen to hydrogen, carbon to hydrogen. You'll get to know this one, the carbon to oxygen double bond. It should stand out big time. So alkanes, we have CH2 to CH2 bond, which is down there at 1450. And alkanes are the only ones that have that massive peak at 2,900. So you have your carbon to carbon bonds over on the right-hand side here. And if we go back to, okay, carbon to carbon, that's carbon to carbon. I'm going to give you carbon to carbon, it's not very nice. So carbon to hydrogen, you should see a peak at 2,720 and 3,100. Whoa, look at that. We have a peak there. But we don't really have a peak anywhere else aside from that CH2 to CH2 bond on the right side. Alkenes are slightly different. So we've got this alkyl compound, which is just alkanes, vinyl, which is alkenes, an alkanol, which should be an alkene. But again, you're never going to be asked to differentiate between an alkane, alkene, and alkyl. So again, I wouldn't worry too much about the alkanes, alkenes, and alkynes. Never seen them assessed. They like to go for the more complicated ones. Again, aromatics have 3 carbon to carbon double bonds. Which show up as this sort of peak here. But again, I don't think they're going to go for that. We'll get into the real ones. Okay. Take note. That big dip over here on the left-hand side tells us there is an OH bond. Depending on whether it's primary, secondary, tertiary, or attached to an aromatic hydrocarbon, will tell you the difference between. But again, you're not given that information in your data booklet, but it's just a good piece of information to know. So take away from this one, we have hydrogen bonding present. So this is why we have this shape here. If you see this shape, you know it has an OH bond, regardless of everything else. So amines, again, we've got a bond on the far left, or a peak on the far left. So we've got what we call the doublet. So that's kind of like, you know, that there's 2 hydrogens attached to a nitrogen on that left-hand side. So if you see that little, looks like a pair of fangs on the left-hand side. Okay, so you see that big yellow dip? So the aldehydes have a carbon to oxygen double bond. If anything has a carbon to oxygen double bond, you will see this down here, this dip. it almost goes to 0. If you're not sure and you go, hey, I can see that there is a carbon to oxygen double bond, but what else is there? Well, you've got this doublet here at 2720 and 2820 that only occur in the aldehydes. Ketones, we have carbon to oxygen stretch down there. And we don't really have anything else of concern. They are the simplest of all of the IR spectrographs. You just have that big dip in the middle, not much else at all. You don't have the double that you have with the aldehyde. So, can you see the difference? Aldehyde, ketone. Almost exactly the same peak for the carbon to oxygen double bond. So carboxylic acid, if it looks messy, it's a carboxylic acid. So we've got this massive dip here that indicates our OH bond. We've also got our carbon to oxygen double bond, and that's how we know it's a carboxylic acid. Also has a carbon to oxygen, and one of the practice questions will be a carboxylic acid, and you should be able to pick it up super fast. So esters have carbon to oxygen double bond, they also have a carbon to oxygen single bond at about 1150. Now the next slide. So amides. Remember in the amines how we had the pair of fangs? With the amides, we get the double pair of fangs. And we've also got, which indicates nitrogen bound to hydrogen. 2 hydrogens, 1, 2. And at 1650, we've got our carbon to oxygen stretch again. I want everybody to draw these, and if you try to remember just the numbers, you will go insane. If on the left hand side above, so if you go above 3000, that's where we're looking. Everything else before that is just carbon to carbon, carbon to hydrogen. So if we see this broad U-shaped peak, we have an oxygen to hydrogen bond. If it's a needle shape above 3000, we've got a triple bond carbon to carbon. So we've got either the single fangs or the double fangs for amines and amides. And if we look just above 3000, and there's a peak there, we'll see a carbon to carbon double. Okay. I'm not sure if we're going to do spectroscopy. Can't really speak yet. So here we see sharp needle-like spike gives us our nitrile group, or carbon to nitrogen triple bond. You're not actually given this in your formula book, so I can't imagine they will ask you about it. So in this region, we've got oxygen to hydrogen, nitrogen to hydrogen, and carbon to hydrogen. So if we see something out there, we know it's not a simple molecule. Again, just the numbers. So for propanoic acid or any carboxylic acid, we've got our oxygen and hydrogen stretch out here. And we've got our carbon to hydrogen bonding just before 3000. And then we've also got our carbon to oxygen double bond here. Esters, carbon to hydrogen, carbon to oxygen double bond, carbon to oxygen single bond. This is one of those things that you learn by exposing yourself to it a lot. I'm going to give everybody 30 seconds, actually 2 minutes to come up with a solution for what this is. You're given the molecular formula, so that should give you some idea of what it is. I'm just going to quickly make coffee in the 2 minutes you guys are looking at this for. Okay, any ideas? What can we see? So here we've got our our oxygen and hydrogen stretch. Here we've got carbon to oxygen double bond. Almost touches the bottom. It's just about bang on in the middle. And this looks messy as heck, right? We've also got carbon to oxygen single bond here. So that is a carboxylic acid. So I'm going to give you guys 60 seconds to have a think about this. So looking at the formula, it can be one of three things: an aldehyde, ketone, or an alcohol. If it was an alcohol, we would see a big dip here. So it's not an alcohol. So it's either an aldehyde or a ketone, because we can see the big carbon to oxygen double bond bang in the middle. But what we have here is our carbon to hydrogen stretch that we have in our aldehydes. So what would this one be? Everyone, 60 seconds. It should be fairly obvious just from the name or the formula even. So it's going to be an amide, because we have nitrogen and oxygen. If it was just N, it would be an amine. But we can also tell that by carbon to oxygen double bond here, and our double fangs for our amides. So this is why it's important. If all you learn is what the shapes are supposed to look like, you know, from 2600 and above. Ethanoic acid, propanol, we have the carbonyl, and then the little CH group. In a ketone, we wouldn't have that. We just have the carbon to oxygen double bond. So the amide, we had the carbon to hydrogen group, the carbon to carbon group, but again, that's not really on the left-hand side. And we had the nitrogen to hydrogen amine group, but it's an amide because we've got the carbonyl group. All right, I'm going to send you guys these questions. I can't talk anymore. I do apologize. I'm going to have to do this in about 13 or 14 recordings. I went to the doctor and they said it'll hopefully get better on its own. It's just a very irritated throat from talking with a cough for so long. So there's 2 pages of questions. I want you guys to have a go at them. And then I'll upload this recording and send it out straight away. Have a go at the questions. And then we'll go through them next week. I will see you guys next Tuesday and we'll go through these questions.